National Electrical Code Section 250.32 Bone and 250.32b2 address different scenarios regarding equipment granting conductors. Section 250.32 Bone mandates that an equipment granting conductor, or EG, shall be run with the supply conductors. This requirement applies when the equipment grounding conductor is part of the service entrance conductors. The reason for this requirement is to ensure a low impedance path for fault currents to return to the source. A low impedance path is crucial for the fast operation of overcurrent protective devices like circuit breakers or fuses. This quick operation is essential for safety, minimizing the duration of potentially dangerous fault conditions. Section 250.32b2, on the other hand, addresses situations where the equipment grounding conductor is not part of the service entrance conductors. In these cases, the code permits the equipment grounding conductor to be run separately from the supply conductors. However, this is conditional, and the installation must comply with the specific requirements outlined in 250.32b2. A common scenario where the equipment grounding conductor is run separately occurs when a subpanel is fed from a main panel. In such installations, the equipment grounding conductor for the subpanel can be run independently from the supply conductors. The key condition here is that it must be connected to the equipment grounding conductor busbar within the main panel. To elaborate further, consider a typical residential electrical system. The main service panel receives power directly from the utility company. From this main panel, subpanels might be installed to serve specific areas, such as a detached garage or an addition to the house. When feeding these subpanels, the National Electrical Code allows for some flexibility in how the equipment grounding conductor is handled. Now, let's dissect the requirements of 250.32b2 in more detail. The code provides several options when an equipment grounding conductor is not run with the supply conductors to a separate building or structure. One option involves grounding the equipment grounding conductor to a ground rod or other approved grounding electrode system at the separate building or structure, while also ensuring a continuous metallic path back to the main panel. This metallic path can be achieved through metallic conduit or other approved means. This continuous metallic path is crucial for maintaining a low impedance fault current path. Another option allowed by 250.32b2 is to use the grounded circuit conductor neutral for grounding purposes at the separate building or structure, but only under very specific conditions. These conditions typically involve ensuring that there are no other metallic paths between the buildings. It's important to note that this option is less common due to the restrictions and potential safety concerns associated with using the neutral conductor for grounding. In general, it is best practice to always run a dedicated equipment grounding conductor with the supply conductors, especially when dealing with sensitive electronic equipment. To further clarify the relationship between 250.32 Born and 250.32b2, consider these points. Firstly, 250.32 Born is the default requirement. It mandates that an equipment grounding conductor must be run with the supply conductors when it is part of the service entrance. Secondly, 250.32b2 provides exceptions to this rule, allowing the equipment grounding conductor to be run separately under specific circumstances. Thirdly, these exceptions are not intended to be loopholes. They are designed to address specific situations where running the equipment grounding conductor with the supply conductors is not practical or necessary, while still ensuring electrical safety. It's important to remember that electrical codes are in place to protect people and property from electrical hazards. Therefore, it is crucial to understand and follow the code requirements carefully. When in doubt, always consult with a qualified electrician or electrical inspector. They can help you determine the best way to ground your electrical system and ensure that it meets all applicable code requirements. Let's delve deeper into the importance of a low impedance fault current path. When a fault occurs in an electrical system, such as a short circuit, a large amount of current flows through the system. This fault current needs to be quickly and safely directed back to the source so that the overcurrent protective device can trip and energize the circuit. A lower impedance fault current path allows this to happen quickly and efficiently. If the fault current path has high impedance, it will impede the flow of fault current. This can result in a slower tripping time for the overcurrent protective device, which can increase the risk of electrical shock, fire, and equipment damage. The equipment grounding conductor plays a crucial role in providing a low impedance fault current path. It is a dedicated conductor that is specifically designed to carry fault current back to the source. The equipment grounding conductor is typically made of copper or aluminum and is sized according to the requirements of the National Electrical Code. In addition to the equipment grounding conductor, other metal parts of the electrical system, such as metal conduit and metal enclosures, also contribute to the fault current path. It is important to ensure that these metal parts are properly bonded together to create a continuous and low impedance path. Bonding is the process of connecting metal parts together to create an electrically conductive path. This can be done using bonding jumpers, bonding screws, or other approved methods. Proper bonding is essential for electrical safety. Now let's discuss some common mistakes that people make when installing equipment grounding conductors. One common mistake is to undersize the equipment grounding conductor. The National Electrical Code specifies the minimum size of the equipment grounding conductor based on the size of the circuit conductors. It is important to follow these requirements carefully. Another common mistake is to not properly bond the equipment grounding conductor to metal parts of the electrical system. This can create a high impedance fault current path, which can compromise electrical safety. Another mistake involves using the neutral conductor as the equipment grounding conductor. While this is permitted under very specific conditions, it is generally not recommended. Using the neutral conductor as the equipment grounding conductor can create a shock hazard if the neutral conductor becomes open. To summarize, National Electrical Code sections 250.32b and 250.32b2 provide guidance on the installation of equipment grounding conductors. Section 250.32b requires that an equipment grounding conductor be run with the supply conductors when it is part of the service entrance. Section 250.32b2 provides exceptions to this rule, allowing the equipment grounding conductor to be run separately under specific circumstances. It is important to understand and follow these requirements carefully to ensure electrical safety. Always consult with a qualified electrician or electrical inspector if you have any questions or concerns. They can help you determine the best way to ground your electrical system and ensure that it meets all applicable code requirements. Remember that electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others from electrical hazards. Understanding the National Electrical Code and following its requirements is a critical step in ensuring electrical safety. Furthermore, let's discuss the significance of impedance in electrical circuits. Impedance is the measure of opposition to alternating current, similar to resistance in a direct current circuit, but also includes the effects of inductance and capacitance. A low impedance ground path is critical for safety because it allows for a rapid fault current flow, ensuring that overcurrent protection devices like circuit breakers trip quickly. This rapid response minimizes the duration of a fault, thereby reducing the risk of electrical shock, fire, and equipment damage. High impedance, on the other hand, restricts the flow of fault current, potentially delaying the activation of overcurrent protection and increasing the hazard. When considering grounding systems, it is important to recognize that the goal is to create a low impedance path back to the source. This is achieved through proper selection and installation of grounding conductors, as well as effective bonding of metallic components within the electrical system. Bonding ensures that all metal parts are electrically connected, creating a continuous, low impedance path for fault currents. The size and material of the grounding conductor also play a vital role in achieving low impedance. Grounding conductors are typically made of copper or aluminum and must be sized appropriately based on the size of the circuit conductors they serve. The National Electrical Code provides specific tables and guidelines for determining the correct size of grounding conductors. In addition to conductor size, the length of the grounding conductor also affects impedance. Longer conductors have higher impedance, so it is important to minimize the length of grounding conductors whenever possible. This can be achieved by strategically locating grounding electrodes and by using shorter runs of conduit and other metallic pathways. Moreover, it's important to consider the impact of corrosion on grounding systems. Corrosion can increase the impedance of connections and conductors, compromising the effectiveness of the grounding system. To prevent corrosion, it is important to use corrosion-resistant materials and to protect connections from moisture and other environmental factors. Regular inspection and maintenance of grounding systems are also essential for identifying and addressing any potential corrosion issues. When installing grounding electrodes, it is important to ensure that they are properly driven into the ground and that they make good electrical contact with the earth. The National Electrical Code specifies minimum requirements for the depth and spacing of grounding electrodes. It is also important to consider the soil conditions when selecting and installing grounding electrodes. Soil resistivity can vary significantly depending on the location, and it is important to choose grounding electrodes that are appropriate for the soil conditions. In areas with high soil resistivity, it may be necessary to install multiple grounding electrodes to achieve the desired grounding resistance. The National Electrical Code also addresses the use of supplemental grounding electrodes. Supplemental grounding electrodes are additional grounding electrodes that are installed to improve the overall grounding performance of the system. Supplemental grounding electrodes can be particularly useful in areas with high soil resistivity or in situations where sensitive electronic equipment is being used. When installing supplemental grounding electrodes, it is important to ensure that they are properly bonded to the main grounding electrode system. This will ensure that all of the grounding electrodes work together to provide a low impedance ground path. Furthermore, it is crucial to understand the difference between grounding and bonding. Grounding is the connection of an electrical system to the earth, while bonding is the connection of metal parts together to create an electrically conductive path. Both grounding and bonding are essential for electrical safety. Grounding provides a path for fault currents to flow back to the source, while bonding ensures that all metal parts are at the same electrical potential, reducing the risk of electrical shock. The National Electrical Code provides specific requirements for both grounding and bonding. It is important to follow these requirements carefully to ensure electrical safety. When installing electrical equipment, it is important to ensure that it is properly grounded and bonded. This will help to protect people and property from electrical hazards. Always consult with a qualified electrician or electrical inspector if you have any questions or concerns about grounding and bonding. Now let's discuss the importance of equipment grounding conductors in specific applications. In healthcare facilities, equipment grounding conductors are particularly critical due to the sensitive nature of medical equipment and the increased risk of electrical shock to patients. Healthcare facilities often have stringent requirements for grounding and bonding to ensure the safety of patients and staff. In industrial facilities, equipment grounding conductors are essential for protecting equipment from damage caused by electrical faults. Industrial equipment often operates at high voltages and currents, so it is important to have a robust grounding system in place to quickly clear any faults. In residential settings, equipment grounding conductors are important for protecting people from electrical shock. Ground fault circuit interrupters, or GFCIs, rely on a properly installed equipment grounding conductor to function correctly. GFCIs are designed to detect small differences in current between the hot and neutral conductors and to trip the circuit if a ground fault is detected. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs can help to prevent electrical shock by quickly de-energizing the circuit in the event of a ground fault. Therefore, a properly installed equipment grounding conductor is essential for the effective operation of GFCIs. In conclusion, understanding the requirements for equipment grounding conductors is crucial for electrical safety. National Electrical Code Sections 250.32b and 250.32b2 provide guidance on the installation of equipment grounding conductors in various situations. By following these requirements and consulting with qualified professionals, you can help to ensure that your electrical system is properly grounded and bonded, protecting people and property from electrical hazards.